Good. Well, good afternoon, everyone. This is a reprise of a talk, but expanded a bit, that I gave originally to the MSIG group. And more recently, I've given a slightly longer version to the IET Sussex branch. So you should be able to see that on YouTube eventually if you're still interested. But I'm going to talk to you this afternoon about Moonshine. And this was a World War II jammer. So by way of introduction, modern radars use very complex systems to monitor the radar environment. They can identify potential threats and determine appropriate electronic responses. And if the aim is simply to deny the enemy the use of a radar, the most effective form of jamming is noise jamming, which retransmits a noise-like waveform into the frequency band of the radar. If the exact frequency is unknown, then a broad band of frequencies is used, what's known as barrage jamming. However, this sort of jamming should normally, not always, but be fairly obvious to the enemy that jamming is taking place, which may not be a desirable outcome. And a more sophisticated form of jamming is deception jamming, which aims to recreate realistic false targets. And it's a more sophisticated form of attack, which the enemy may not be aware, initially at least, that this is happening. Against pulsed radars, repeater jammers can be used. These receive individual radar pulses and in a modern system temporarily store them for a few microseconds or less in a very high-speed digital RF memory. They then transmit them with added modulation in time and frequency as desired. And their aim is to recreate a radar false target or a collection of targets in order to distract or deceive the radar. However, that's a modern system. We shall see in this talk that radar jamming is not new and is almost as old as radar itself. And so I'm going to talk about the first British jammer, which is in fact a pulse repeater jammer, that entered service in World War II in 1942. So the first operational radars in the UK were developed in the late 1930s. The radar known as the Air Ministry Experimental Station No. 1, Ames 1, later known as Chain Home, entered service in 1938. And the first experimental monostatic airborne radar flew in 1937, with the first operational airborne radars deployed soon after the start of World War II in 1939. So in the picture on the display here, we can see ASV Mark II on a Wellington of RAF Coastal Command, Ames 1, the Chain Home, and this is Chain Home Low, a higher frequency version to get lower altitude targets, Ames Type 2, and then this ground control intercept radar, slightly later, but still 1940s, about 1940, the Ames Type 7 ground control intercept radar. These are all VHF, well, these are VHF radars. This is actually an HF radar, the Chain Home. So these three, the Chain Home and the ground control intercept, were used for air defense, and the ASV systems were used for hunting U-boats and ships. But so by 1941, there were many British radars in service. But radar countermeasures were a low priority, and there was really quite limited understanding of German radar capability. But then in 1942, there was a rude awakening in the form of what was later called the Channel Dash, where two German battle cruisers escaped up the British Channel, the English Channel from Brest to the safety of German ports. And they did this under cover of heavy jamming attack against the British coastal radars. And here we can see a picture of a long line of German ships led through the channel by the Scharnhorst, Gneisenau, and the Prinz Eugen. As a result of this jamming attack on the British radars, the Radio Countermeasures Division at the Telecommunications Research Establishment, this division led by someone called Robert Coburn, were then able to establish radar countermeasures as an essential war requirement. And two jammers aimed at the German air defense radars along the coast of France, which I'll explain to you in a minute, were rapidly developed. And these first jammers were airborne. There was a barrage noise jammer called Mandrel, and a pulse jammer, which was the first into service, called Moonshine, the subject of this talk. But as I mentioned earlier on, in these early years, there was very little knowledge of German radar capability. In fact, many in government and scientific circles doubted that the Germans had radar at all. However, they were getting increasing reports from spies, interrogation of prisoners of war, and intercepted radio traffic, which suggested that they must have what was known to the British as RDF, radio direction finding, or DT in German, decimeter technology. And it was thought from the reports they were getting that one of these systems might be called Freya, who was a German mythological goddess. And so now the hunt was on for pictures of these systems and indeed reception of their signals. And a breakthrough came on the 22nd of February, 1941, when two Freya radar stations were photographed at Hauteville in France. And you can see here the picture that was actually taken, and we can see these two square arrays facing different directions, vertical antennas, and these were recognized as radars, probably the Freya, and the first signals from these systems were identified at about the same time from listening stations operating on a frequency of about 120 megahertz. And on the 5th of December, 1941, further pictures of a radar installation were taken at Cap d'Antifer, near Le Havre in northern France, in a village called Bruneval. And these showed the Freya here. These are the cliffs, just on the coast. And then here, this little dish here was what they subsequently learned was a Würzburg. And as time went on, a much clearer picture of German radar was being developed. And this culminated on the 27th to 28th of February 1942, a few months later, in the famous Bruneval raid, when British commandos captured a Würzburg, this little radar here, and brought it back to the United Kingdom. And they learned a huge amount about the German radar technology, and realized that in fact they'd had radars operating from right at the beginning of the war. It was becoming clear that the German air defense system comprised long-range Freyas, these systems here, and then shorter-range fighter control radars, the Würzburg. And I'll give you a bit more details about those in a minute. So what was going on in 1942 over in the continent? The Germans had occupied France and the Netherlands and Belgium, and the Royal Air Force were attempting to gain air superiority over France, flying from the United Kingdom. And it had been determined by then that from aerial reconnaissance and signal intercepts and so on, that there was a complete chain of coastal radar stations, as shown on this map. Each of these dots represents a German air defense radar station. Each of these stations had one or more long-range Freya air defense radars and a shorter-range Würzburg fighter control radar. And they were spaced apart sort of 25 to 50 miles. And at this stage, it was decided by the British to attempt to spoof the Freya systems using airborne jammers. And the intention was to give the impression of an approaching raid of bombers to divert the German fighter defenses away from true bomber raids coming in a different direction. So I'll just say a bit about the German radars themselves. The radar to be jammed was the Freya, and this operated within a frequency band of about 119.5 to 128 megahertz at this stage. Pulse length of about 2 microseconds, receiver bandwidth of half a microsecond or half a megahertz or so. The Allies hadn't captured any examples of this radar, and other parameters had to be estimated from photographs and signal intelligence reports. And the figures shown here of the pulse repetition frequency, antenna gain, and so on, were the estimates at the time. They were pretty close. It actually had a peak power of about 10 kilowatts. It was determined from intercepted radio messages that the Freya could detect a fighter aircraft out to about 120 miles. The Würzburg was a higher frequency system operating on about 570 megahertz. It had a shorter range capability than the Freya, and perhaps about 35 miles against a fighter aircraft. So it was important that aircraft carrying any jammers to jam the Freyas were kept at least 35 miles away from the Würzburg, so that their deception couldn't be unmasked by this system. This is what they look like. This is a Freya, a transmit antenna at the bottom and a receive antenna at the top. And this is the Würzburg. You can see from the people the sort of scale of this equipment, about a 3-meter antenna. There was also a giant Würzburg, which was not very common at that stage, but more of them came in during the war. This had a more than twice the diameter aperture, a very large aperture. And that had a range of about 70 miles. But the radar interest was this Freya. And this is an example. This is what was known as a limber Freya, which could be easily transported to different sites. And in this, at the bottom here is the operator's cabin, 2 operators. They could steer the beam by hand, turning a large wheel, and they would search over an arc, and when they received a signal, they would turn the antenna for maximum gain to determine the bearing. Later on, they used a split beam on receive in order to do essentially sequential lobing, if you like, to get a bearing, a more accurate bearing estimate. So each of these arrays was 6 vertically polarized dipoles with a mesh reflector. So it's worth visiting here the Jammer radar equation as applied to Freya. A pulse jammer needs to replicate the power density received at the radar from a real target. So we can see here that this is the effective radiated power, the peak power times the directional gain of the radar, PRGR. And at the target at some range R, the power density is 4 pi PG over 4 pi R squared. And then if the target has a radar cross-section sigma, essentially the ERP of the signal returning back to the radar is given by this expression here, standard radar range equation stuff. And so the jammer ERP is going to have to match the reflected signal from the target if it's protecting itself at the same range. And so the jammer ERP only has to be of some fraction k of the radar ERP. If we plug some numbers in with a radar cross section of 100 meters squared, R of 35 miles, the shortest they were going to have to get to, it can be seen that k is actually about minus 86 dBs. So plugging in the numbers for Freya, and using a jammer with perhaps a 3 dB antenna gain, sort of a hemisphere, that tells you, these sums tell you that the transmitter peak power only needs to be 0.5 milliwatt in the jammer, and indeed even less power required at longer ranges. So even allowing for significant feeder losses and atmospheric losses and things like that, the jammer power of only milliwatts is going to be required. As I mentioned just now, at that time, the parameters of Freya had to be estimated from aerial photographs and signal measurements. And a number of calibration flights were made to establish the signal levels received from Freya at different ranges and altitudes. It was also recognized it would be necessary to retransmit a signal with the power proportional to the received signal, with an appropriate gain, which they estimated to be about 34 dBs to represent the return from a bomber. And so for 30 millivolts received, which was what they were expected to receive at a range of about 35 miles with a quarter wave dipole, they would need to transmit a signal of about 1.5 volts at the antenna, which represented a maximum required power of about 30 milliwatts. So the idea was to fit this new jammer into a group of aircraft flying at about 10,000 feet towards the enemy air defense system, starting from a range of over 100 miles. Each aircraft would have one Moonshine equipment tuned to a spot frequency within the band of frequencies used by Freya. And then each Moonshine would transmit an extended pulse of up to 50 microseconds long on receipt of a radar pulse within the bandwidth of about 1 megahertz to which it was tuned. And to cover the full band of frequencies occupied by different Freyas, about 8 sets in separate aircraft were needed to ensure full coverage. This is how it was done. A simple block diagram. There was a receiver, a pulse unit, and a transmitter. If a pulse was received within the band to which the receiver was tuned, it was mixed down to an intermediate frequency, 20 megahertz, amplified, detected, and used to trigger the pulse unit here. And the pulse unit, here's the pulse from the receiver. That would be up to perhaps typically a 2 microsecond pulse from the radar. There was a limiter to limit the maximum amplitude of the pulse, short delay, and then this triggered a master pulse generator, which had a pulse length of up to 50 microseconds, which was going to be the length of the retransmitted signal. And then this, in turn, this was used to switch on an array of oscillators. This was 3 transitron oscillators with neon sawtooth oscillators going on in the background, slowly varying the frequency of oscillation. A transitron is essentially a single valve multivibrator. And each of these transitrons had a slightly different oscillation frequency of about 300 kilohertz and different phases. So they mix together to give a pulsating, noise-like waveform with a restricted bandwidth, and this resulting signal, up to 50 microseconds long, was then amplified in this what we call a memory automatic volume control. So this was the measured magnitude of the incoming signal was used to modify the magnitude of the outgoing signal, which was then used to modulate the transmitter. And so you've got the transmitter has a simple local oscillator, and then a frequency doubling transmitter valve, which was anode modulated by this noisy waveform from the pulse unit, and then out to a simple quarter wavelength dipole, which was also connected back to the receiver. There was a high-pass filter to stop the receiver being triggered on the intermediate frequency of 20 megahertz. And the pulse unit, as well as triggering the oscillators, also suppressed the receiver on receipt of a pulse and turned on the transmitter. So Moonshine was first fitted on Boulton Paul Defiant aircraft, as shown here, with the first operational mission in July 1942. And these were assigned to what was known as a Special Duties Flight, later 515 Squadron, as part of RAF Fighter Command. This is originally a fighter aircraft aimed at attacking bombers, but it wasn't very successful and was replaced by better aircraft for that role, but was used for jamming missions. This is what the hardware looked like. The transmitter and receiver were in the HF unit here, and there was a power unit, power supply, and then the pulse unit. And looking in the pulse unit, you can see this is the row. These are the 3 transitrons. And you can just see the neon tubes behind as part of the oscillation system. These equipments were sort of handmade, if you like to call that, in the workshops at the Telecommunications Research Establishment, and probably only tens of them would have been made. And as far as we know, none have survived for the present day. Here's just a closer look at the technology, the receiver section. This is the receiver, the IF strip, the local oscillator and mixer. And you can just see down here the little diode thermionic valve detectors. And this is looking underneath of the pulse unit. And there was a variable delay, which could be preset, and then also a modulation switch, which controlled the depth of modulation to simulate different densities of aircraft. And here's the technology of the transmitter, just a simple EF50 valve, known as VR91 in those days, the oscillator, local oscillator for the transmitter, and a high-pass filter. And this is what the spoof signals would have looked like. They could be up to 50 microseconds long, as I said. And it was estimated that this was the maximum range extent before adjacent Freya systems would report obviously different bearings of the targets. And you can see different A and B of the different modulation depths. These were reproduced on a British chain home system, chain home low, which operated on a similar frequency. This is range against amplitude down like this. This is the way they displayed things in those days. And this is actually a return from 30 Spitfires. This is a real signal, 30 Spitfires in a 5-mile raid. And this is a little simulation I did just to show the sort of signal that an operator might have seen. And so the early uses of Moonshine were very successful. Enemy fighter squadrons were scrambled to meet phantom threats, allowing real raids to proceed with a reduced threat. Of course, once the Germans realized what was happening, inevitable protection measures were put in place, and the spread of frequencies was increased in the Freya systems. And further Würzburg Riese, the large Würzburgs, were introduced. The equipment was refitted in Beaufighter aircraft, a picture of a Beaufighter here, but the requirement to jam Freyas in this way was no longer required after about April 1943. But the mandrel system continued to be very important to protect bomber raids over Germany. Work did start on a 55-centimeter version of Moonshine, which could be used to counter the Würzburg, but this was discontinued soon after. But we'll come back to some of the advanced ideas that were developed at this time in a later version. So Moonshine wasn't used to spoof Freyas after April 1943. However, the equipment was soon needed again as the Allies planned for Operation Overlord, also known as D-Day, the invasion of France. Now, the intention was to spoof enemy airborne maritime surveillance radars, so not ground-based radars anymore, but they're airborne maritime surveillance radars, which were used to hunt for and attack shipping. And the idea was to give an impression of a long line of approaching ships to cover the planned seaborne invasion across the English Channel. And this would require equipment operating on different frequencies, but now also manned by operators. The threat now is normally just a single airborne radar at any one instance, rather than multiple Freyas on different frequencies. So the Moonshine could be tuned by an operator listening on headphones to the required frequency of intercepted signals. It was intended to use it simultaneously with aircraft dropping window, which is chaff. I'll show you a picture of that in a minute, that could be used to simulate large ground-moving ship convoys in ground-based radars. And as we shall see, the same equipment was also successfully used slightly later in 1944 in support of Operation Dragoon, which is where the Allies invaded southern France. So the naval version of Moonshine was called the Type 660, and the main threat was the FUG Funkgerät 200 Naval airborne radar, which operated in a frequency range of 540 to 590 megahertz. I'll show you this in a minute. There were also expected to be threats from VHF radars, such as the Liechtenstein S, and also they thought they may have captured British VHF ASV systems and be using those. So I'll show you one of these British systems now to help explain the German system. This was a British ASV Mark II. This is on a Hudson, And essentially, these radars used a forward-looking transmit antenna with a fixed beam and two receive beams squinted left and right. So you'd send out a series of pulses from the transmitter, and then the receiver would switch between left and right receive antennas over perhaps a 20 millisecond dwell, and compare the amplitude of returns from left and right. And when a target was dead ahead, the amplitude of the returns would be equal. And the aircraft would be steered under control from the radar operator to point at the target. And this is the sort of antennas they were using. And this is the FUG 200 Hohenwald, which operated at higher frequency than the British systems. They were on British systems were about 176 megahertz, but it used a very similar system. And we think they almost certainly copied this from captured British equipment. So a forward-looking transmit antenna, and then two receive antennas like this. And the receiver switched rapidly between alternate antennas, again comparing the amplitudes to give an indication of bearing. The eagle-eyed amongst you might have noticed this Junkers 188 with the radar on it has an RAF roundel. This was because it was photographed in 1945 at RAF Brize Norton, where it was being evaluated following capture at the end of the war. And these are the radar parameters. I'm not going to dwell on these, but it had a very high peak power for this time, this UHF frequency, achieved using a thyrotron, but also a very low PRF, only 50 pulses a second, which meant its mean power actually was quite low. The British didn't use airborne radars in this frequency range at all during the war, but the UHF airborne radars were developed in the United States. This is what it looked like. This is in the cockpit of the Junkers 188. Here is the control column, and here is the radar indicator. And you can see here a patched up bullet hole in the canopy. And this is a close-up of the display unit. It was just a 2.5-inch cathode ray tube with a magnifying lens giving 2:1 magnification. And this is a simulated L-scope response that they would have seen, range running up the screen here, and then left and right antenna responses showing us responses to the left and right of the time-based line. And a target dead ahead like this one would show equal left and right. So this new naval system was brought into service to spoof these German radars, as well as operating on different frequencies to the earlier system and having a number of different frequency options. The principal change was now the equipment was controlled by an operator. Also, they removed the automatic volume control memory circuits so that they weren't responding with a signal proportional to the received signal because of the problems with multipath fading at the sea surface. So they retransmitted a fixed amplitude signal. And here is the Type 660 in 4 boxes with different plug-in units or different versions for different frequency coverage. And this was fitted to Harbour Defence Motor Launches, HDML. And United States Army personnel were specially selected and trained as operators by the Telecommunications Research Establishment Post-Design Services Team, PDS. And now an operator would tune across the band, and on receipt of a threat signal, tune the transmitter to the same frequency. And usefully, perhaps the Hohenwald had a 50 hertz PRF, which I mentioned, which would have been quite distinctive, allowing discrimination against ground-based Würzburg and so on, which had PRFs closer to a kilohertz. And then during Operation Overlord in June 1944, the Moonshine equipment was used in 2 naval operations, 2 naval diversions, one called Taxable in the Cap d'Antife region, which we mentioned earlier, near Bruneval, and Glimmer in the Boulogne region near Calais, both to divert the enemy from the real invasion in Normandy. And then during Operation Dragoon in August 1944, Moonshine equipment was used in 2 naval diversions on different days. One in La Ciotat Bay and one near Nice. And in this occasion, 5 of these harbor defense motor launches were used, with Moonshine sets covering a number of different UHF and VHF frequencies. And also carpet noise jammers and Wellington aircraft dropping window to confuse the Würzburgs and ground-based radars. And here's a picture of some window. These are metallized strips tuned to the radar frequency. And here's a picture from an early manual of a carpet UHF noise jammer. So Moonshine was available in various versions by the end of 1944. British ones built by TRE in very small numbers. There was also an American version, AN/APQ-15, covering different frequency bands aimed at spoofing the Japanese radars in the Pacific War. And I mentioned earlier on that some work had been done in 1943 on a UHF system, actually at the EMI research labs at Hayes. That had been discontinued, but some of the advanced ideas were taken forward in this American AN/APQ-15. And here's a picture of this repeater jammer. There was a plug-in RF section here, mixing down then to a common IF centered on 15.5 megahertz. And then the received signal was modulated and extended by using a pair of quartz delay lines. And here you can see this is the delay lines, about 2 inches high and an inch in diameter. Here is an X-cut quartz crystal, and then the 15 meg signal would be applied to this, and this would launch signals into this liquid inside the tube here, which was xylene. And then signals were reflected off these edges shown here and below, and back onto the quartz crystal. Because of the speed of propagation through this xylene liquid, this would give an extended response of up to about 50 microseconds. In order to, there were 2 of them on slightly different frequencies, so they would mix together to give a fluctuating signal. But also there was a heater, and this was used to heat the xylene to cause variations in propagation frequencies within the liquid, which also gave the sort of breathing and fluctuating effect that you saw in my earlier simulation. So this is probably the first true pulse repeater. So in conclusion, these British equipments were built in small numbers by TRE, first used to confuse freighters and later airborne maritime reconnaissance aircraft based on ships. They were very effective when first used, resulting in changes to enemy equipment and tactics. So the freighters increased their frequency range, and the Hohenpfeil introduced the ability to rapidly tune to another frequency at a flick of a switch. But in response to all that, work was underway at the end of the war to introduce panoramic jammer receivers with motorized tuning, allowing and work on rapid identification of new signals and automatic tuning to match their frequency. And work had also started on methods to identify radars from their emissions. And of course, this work continues to the present day. So if anyone's interested, I've published articles on ASV Mark I, Moonshine, and the Hohenpfeil in the IEEE AES magazine. So that's the end of the talk. I'm very happy to take any questions if anyone's got any.